So before getting into the actual measurement we would like to do, we need to first discuss what is the thing we actually would like to measure. So what we'd like to understand is what is causing this accelerated expansion of the universe. We call that dark energy, as I mentioned, but we don't really know what it is. So we need to parameterize it somehow, and for that purpose, we need something called the equation of state parameter. So what is it? So this is the Friedmann equation we have seen before. This is telling you how quickly the universe expands. If you know what's inside, this rho is the energy density inside the universe. But the key to this is that how does this energy density change over time? If you remember the discussion of inflation, if the energy density is constant, then the universe would expand exponentially. That's the consequence of a constant energy density. On the other hand, energy density for most things would go down as the universe expands because as the volume gets bigger, things are thinned out and you have less and less energy density. So that is described by a parameter called equation of state. So energy density is related to pressure by an overall proportionality constant called W, and this W is the equation of state parameter. For the gas of photons, which we call radiation, W is 1/3. For usual matter, like atoms, or also for dark matter, W is actually 0. On the other hand, if the vacuum has energy, the constant energy density from this bubbling quantum effects we talked about before, then W will be -1. And depending on the values of W, you may either decelerate or accelerate the expansion of the universe. And if you work out the math, you'll find that W needs to be less than -1/3 for the universe to get accelerated or speed up. And that's shown from this equation. This is called first law of thermodynamics. And by solving this equation, you find that energy density goes with the size of the volume, which has this exponent. So if W is -1, that cancels 1 exactly. So the exponent will be 0, which means the energy density is constant, and that corresponds to vacuum energy. On the other hand, if W is 0, you find -3 in the exponent, namely this is 1 over volume. And that's exactly what you would expect for matter. If we make the universe bigger, the matter thins out as 1 of the volume. So this equation of state parameter W really tells you how quickly a component of energy would thin out, and that in turn, combined with the Friedmann equation, tells you if the universe is going to accelerate or decelerate. And this second derivative, namely acceleration of the universe, goes with 1 minus 3W with an over minus sign. So if W is -1/3, this combination vanishes, then there's no acceleration. If W is less than -1/3, this combination is positive with a minus sign in front, so the universe would accelerate. So that's what happens as a consequence of these equations. And the case when the universe is going to end would correspond to W less than -1. So if W is less than -1, then what happens with this is that, well, this is less than -1, this is less than 0, so then minus with this exponent is positive now. So as the universe expands, energy density actually grows, and that will be the consequence of W less than -1. So if the energy density grows, the universe expands, you just keep feeding in more and more energy that pushes the expansion even further, and that will eventually lead the universe into a big rip. So that expansion becomes so fast that even the galaxies or stars, or eventually even atoms and nuclei get ripped apart, and the universe becomes totally ripped apart and completely empty, and then boom, it ends. You can't even think about what happens next. Universe ends with infinite speed of expansion, and so that is sort of like the end of the universe. On the other hand, if W were slightly bigger than -1, this is a situation very much like what happened at the beginning of the universe, namely inflation. So by measuring this equation of state parameter, this holds the key to predict the fate of the universe, and that's what we would like to measure. So let me show you one video clip here, which is the computer animation that shows what a big rip might look like. So many, many billions of years from now, if we head to a big rip, then this might what happens 200 million years before the big rip.